Hello everyone, welcome back to Google Centers. Yeah, I'm back right now, because I'm so busy because my studies, this is the last semester that I at university and so many projects here. And yeah, I can do recording to you to sharing knowledge about the aerospace. This is but this night or this video, I'm gonna share you about one of my research about acoustic, especially aeroacoustic. Yeah, you know what? But before we go to deep down there, you have to know about what this aeroacoustic means. Aeroacoustics mean the definition of acoustic that I took from aerospace.news.edu. There are acoustics is certainly concerned with the generation and propagations of sound through fluid. It's common cause like a turbulence. This is the common effect cause the turbulence, but that's especially on the um, aero or in the air because turbulence made the noise because the wave there. But in aerospace that Illinois that they do define aeroacoustic is certain centrally concerned with the generation and propagation of sound through a fluid. The prefix aero equals an air, but one can also include sounds in other fluids such as a water. We call hydroacoustic, and acoustic is part of the broader topic of acoustics, and the latter of which can include sound propagation through other types of media, including solids, plasma, and the others. Our research is primarily concerned with generations, propagation, and minimizations, minimizations of sound produced by engineering and biological systems. Through a combination of the theory and computation, we analyze complex systems from a physics-based perspective, usually solving the two or three-dimensional compressible Navier-Stokes equations directly. Yeah, it's so long definition, but the easiest definitions of the acoustics is that's the generations and propagation of sound to a fluid like that. Um, this video, I'm gonna tell you or share you about aeroacoustics analysis. I using a computational fluid dynamic there, CFD, especially the solve versus ANSYS one of of the I analyzed the Airfoil profile NACA 0012. Now we're gonna do the background first. In 2022, right now, development in current research that utilize computational fluid dynamic methods uh, is to simplify the calculations and the complex calculation because we are as the student, as the researchers or practitioner, we use computational method or computational fluid dynamic method to solve the complex things like aerodynamic and aeroacoustics. And there are so many software that we can use, like ANSYS Fluent, Console, SimCenter 3D, and the others software we can use. Uh, and yeah, the second background is assessment of the performance of an airfoil profile is necessary because it affects the aerodynamic and aeroacoustics characteristics. The profile of airfoil makes an effect of the resulting aerodynamic and acoustic result characteristics. So after that, we know that the profile make or there are some effects uh, to the acoustic or to the noise and or the sounds, and yeah, the importance of processing the resulting noise from an airfoil. This is the one of the background. We know the resulting noise is very important to airfoil profile that we made or we choose there, and choose then when we use a like choose a wind turbine or we have to choose a right profile of an airfoil that yeah it's noise minimum, you know, like that. And the after we know the important things is one of the important things are noise. We have to control the noise of that geometry of that airfoil of that object. We have to control that noise, and the first because what? Because if we can't control a noise, it's hard the whole of human ears organs or the others concentration or the other organs. It's uh, yeah effect on us as a human. The aim of this our my research is knowing the effect of angle of attack and velocity on the value of the coefficient of lift HCl and drag and CD of the NACA 0012 airfoil profile. And the second one is knowing the effect of the placement distance of the receiver on the received sound level. And the third one is knowing the effect of angle of attack in the velocity of the control of the static pressure, velocity magnitude, and turbulence kinetic energy that the result of the simulations, and knowing the effect of angle of attack and inlet velocity on sound pressure level, or we call SPL. The scope, yeah, I do the simulation with two-dimensional analysis, and we were carried out with the speed configuration at inlet 10 meter per second and 20 meter per second, and different angle of attack 1, 5, 9, 13, and 70 degrees to know the result of CL and CD. But for acoustic simulation or aeroacoustic for the sound noise level, it's only angle of attack 1, 9, and 17 degrees. The object, okay, the object, absolutely you know about the object. This is the symmetrical profile on NACA 0012, but with chord length 0.12 meter, and the section dimensions is 1.25 meters times 0.5 meters. This is the in the right side, the right hand here. You can see the geometry of NACA 0012. I download this airfoil from airfoiltools.com. Okay, to the next. This is the one of the main research and one of the main video here. It's about the analysis steps. The first one on the analysis step, we call the geometry. Okay. The geometry on there, we entering the geometry of the NACA 0012 airfoil profile and setting the angle of attack and the size of the attack section to be simulated. After after we setting the geometry, after we made the geometry, create the geometry, the next step is meshing. Carry out the meshing process by taking into account the standard that has been determined by my department, my one of the biggest research in Indonesia. Uh, they're giving me a standard quality like orthogonal quality close to 1, skewness quality, skewness close to 0, y plus value is close to 1. These are the standard quality that I do with my research. And after the meshings are according to the I'm sorry, like a standard, uh, and we're gonna do the next step is the setup. During the setup process, I choose the viscose model as a Urans or Urans or something like that, or this is unsteady remote average Navier Stokes. Especially, I choose a K omega SSD model is selected. The acoustic model or acoustic analogy, I choose FWH or Fox Hawkins. Then input boundary condition according to the specific test data, and reference value setting, solution method, and time step. Also, we have to set that time step there. After the setup, after we set up the simulation and we just click run and waiting for the solver to end or to finish to be finished, and yeah, this is the result. The result are compared with the experimental data and CFD's data that has been carried out by other studies or research. But this is the more complex explanation about the geometry simulations. The first import the coordinate of the NACA 0012 Airfoil into the ANSYS design model and connect the coordinates to the line. And second, set the angle of attack 1, 5, 9, 13, 70 degrees. Create a geometry session with dimension of geometry session with dimension of 1.25 meters times 0.5 meters. And the lastly, or fourth, make a split sketch line to make it easier when when we do a meshing on in the meshing steps. This is the meshing result. On the meshing, we have to like set the sizing, like edge sizing, phase meshing, and inflation, and the others, and uh, to result like the standard, the requirement standard of my department. And this is the result of my meshing. Orthogonal quality is 0.98838 and skewness 3 times 7306 times 10 second. No, the uh, 4,000 170 197 for I'm sorry for million I'm sorry for million 190,000 197,862. I don't know, 41978862 element. The element is 1397410, and the y plus value is 1.005491. This is in the right hand here. You can see the meshing result that I zoom to the Airfoil profile at 1 degrees. To the next step is the simulation of setup. We set up in the velocity, absolutely, the 10 meter per second and 20 meter per second, turbulence density 5 meters, I'm sorry, 5%, turbulent viscosity ratio 10, pressure in outlet 0 Pascal, core length of the airfoil is 0.12 meters, then the density, I choose sea level, 1.225 kilogram per meter cube, and the viscosity absolutely I choose here in the sea level is 1.7894 feet. Viscose model here I choose Urans unsteady Reynolds Navier Stokes, and especially K omega SST, and the acoustic model analogy is Fox and Hawkins. The method we choose, not I choose, but that the default of the ANSYS flown is the pressure velocity coupling, and time step number is 1000, and time step size I setting to 0.0005. After we set up that, don't forget to set the main the main what is that the main simulations that wanna be simulate. It's because we simulate acoustic up, and we have uh, to set the receiver locations. The receiver's location. The receiver's is what is the receiver's? First, receiver is one of the thing that catch the sounds like that on sound level. And this is the locations of my receivers. This is the receivers one. This is the coordinate. This is the receiver two, receiver three, and this is the coordinate. After we set up and just click run and waiting a a result. It's, uh, and this is the result of CL and CD, coefficient lift and coefficient drag, of at inlet velocity 10 meter per second and 20 meter per second. But this is it's very difficult to understand this. But I just plot to my Excel and plot that result, and this is the result of lift coefficient compared to NASA and coefficient lift versus angle of attack that I compare to NASA experimental data. The red one is the NASA, and the black and yellow are my compilation of the dynamic simulation. We know that the value of the lift coefficient of the NACA 0012 airfoil has increased, but when entering an angle of 70 degrees, 30 to 70 degrees, there is a state of loss of a lift that, usually we call that as a stall condition here, and at the 13 to 17 degrees. This is the result of coefficient drag or CD versus angle of attack that compare with the NASA absolutely. And yeah, this is the validation of acoustic result by equating the Reynolds number and the angle of attack of the airfoil. The Reynolds number is 170. Why I can't count that? I can spell that. 170,000. 71,232 and 0 degrees. Yeah, I can spell that. And this is the result that we know. The result are increased, but the result is different because what? Because the receiver locations on the experiment, or not experiment, but on the journal that I on the validation data, it's different location of the receivers with my locations or with my simulation or with my research. But the graph it's similar because the increase and down like that. This is the sound quality level versus 1/3 top pin at 19 and 70 degrees at inlet velocity 10 and 20 meter per second. This is the result of that. So it's different result because we change the angle of attack and we change the inlet velocity. It's make a different result of the sound pressure level. This is the contour of the static pressure. This is the velocity magnitude contour. Yeah, at the difference angle of attack and difference in the velocity. Okay, and then this is the turbine kinetic energy at the difference angle of attack also and inlet velocity. Now, because the sound level, sound pressure level value at the one receiver point for its difference angle of attack is caused by the turbine kinetic energy that occurs due to fluid flowing through the airfoil. Because this is the 1 degrees. This is the result of the 9 degrees and 70 degrees. Is there a difference result of the contour? Then this is the sound pressure level graph. It's different because this green are very high than the others result. This is the result of sound pressure level graph show a decrease in the SPL so sound pressure level value when the receiver location is further away from the noise source airfoil. When the receiver's one is more high SPL result than the receiver 3 because the distance or the locations is an important effect to SPL, and this is the result of the effect of the velocity to surface level. And sorry because the sounds it's a noise, but it's not too noise. The conclusions. Well, the first, the coefficient of lift and drag, the NACA 0012 profile tends to increase due to the difference in the angle of attack from 1 degrees to 30 degrees, but when it's changed to the angle of attack 70 degrees experiencing a decrease in the coefficient of lift or we call stall. Second, the distance from the receiver to the sound source effects and the sound pressure level value. The farther a receiver is placed, the lower the SPL value achieved, like that. Uh, Third, the contour of static pressure, force magnitude, and thermokinetic energy have changed due to variation in the angle of attack and inlet velocity. Lastly, in the fourth, the result surface level value changes as the angle of attack and inlet velocity change. Okay, that's all about our sharing session here. In my research, I can't speak to you too much because my English is now decreased. Because I can't. Just busy with my project and my final examinations. That because here I just use Indonesian bahasa or to my daily activity. So don't forget to comment and share this video. Then go to my blogs and my Instagram. Okay, see you.